Hello everyone. Welcome back to our lecture series on forces on trusses. I'm Chaminda and today we are going to learn about the analysis of trusses using analytical approach. As we learned from the previous video, truss analysis can be done by two different methods, that is method of joints and method of sections. Today I'm going to give you an idea about how to analyze a truss using method of joints. Okay, when using this method of joints, there are two different approaches which we can use to analyze a truss. One approach is graphical approach, the other one is analytical approach. So in this video, we are going to learn about the analytical approach to analyze a truss. Now, one of the key theories that we are using for this method, that if the entire truss is in equilibrium, then we know that each of its joints is also in equilibrium. This method is very effective when forces in all the members are to be calculated. So if we need to know the member forces, all the member forces in a truss, then method of joint is the method that we should use to analyze that structure. Okay, let's learn how to analyze a truss using analytical approach. First, I'll explain you the procedure, the steps that you have to follow to analyze a truss using this method. Then we'll do an example so that it will be more clearer to you on how to use this method to analyze a truss. What is the first thing we should do when analyzing a structure? Hope you can remember in my previous lectures we calculated the reaction forces first to analyze structures. Same here, we have to calculate the reaction forces first. How we calculate the reaction forces? We have to use the three static equilibrium equations. So using the three static equilibrium equations, we can calculate the reaction forces. Let's take a truss A, B, C, D, E for this analysis. The truss with 7 members which are unknown, and this truss is supported one end with pin support, that is joint A, and the other end is supported with the roller support, that is joint D is. Three external forces F1, F2 and F3 are applied at joints B and C respectively. So we know that when there is a pin support, there are two reaction components. Here you can see R1 and R2 are the two reaction components at joint A due to the pin support. And we know that for roller support there are one reaction components. So joint D is supported with the roller support, so you can see R3 is the only reaction force at that joint. By analyzing this truss, you can calculate the values for R1, R2 and R3. So calculating R1, R2 and R3 is the first step that we should do. What is the second step? In this method, we have to analyze joint by joint. So once we calculate the reaction forces, next thing is to select a joint, select an appropriate joint and analyze that joint to get the unknown member forces. So how do we select the appropriate joint to start this analysis? Now our step 2 is to select a joint where there should be no more than two unknowns. So if we consider the joints A, B, C, D and E in this truss, let's take joint A. How many unknowns in this joint? Now if I consider the total number of forces, two reaction forces and two member forces from AB and AE. Two reaction forces R1 and R2, we know the value, we know the reaction forces at the joint, but we don't know the forces at members AB and AE. So two unknowns. So we can select joint A to start the analysis. Similarly, if you check joint D, there are three forces altogether acting on that joint. R3, the reaction force, which is a force we know, and two member forces in the members DE and DC. So again at joint D, two unknowns, and we can start this analysis either selecting A or D. What about joint B? If you consider joint B, there are two external forces acting at that joint F1 and F2, and there are three member forces from the members BC, BE and BA. So that joint B, there are three unknown forces, which the joint B we cannot start the analysis with joint B because there are three unknowns. Similarly, if you see joint C, again three unknowns, and when it comes to joint E, four unknown member forces. So as to start the analysis, we should select either joint A or joint D. So I'll select joint A. Once you select the appropriate joint, then the third step is to draw the free body diagram and calculate the unknown forces using the two equilibrium equations. So I can draw my free body diagram to joint A, R1 and R2 reaction forces, and the member forces of member AB is T1 and member force of member AE is T2. Now you may notice that I have marked those member forces as tensile forces. So it is not necessary to assume all the truss members are in tension, but to make more simpler of the calculation, we mark the member forces are as tensile forces and proceed the calculation. Once you get the answers, you can see whether those members are actually under tension or compression. Once you mark all the members as tension and get a positive value, then that member is under tension. But once you mark it as a tensile force, and if you get a minus value, then that member is under compression. So once you draw the free body diagram, you can apply the two equilibrium equations as I mentioned before. So what are the two equilibrium equations for this joint? Total forces in the horizontal direction should be equal to 0 for the equilibrium. Similarly, total forces in the vertical direction should be equal to 0 for the joint equilibrium. So applying those two equations, you can calculate the two unknown forces T1 and T2. Once we obtain the two unknown forces at joint A, the next step is to select the next joint and do the same analysis to obtain the unknown forces at that joint. So the same theory applies when we selecting the next joint, where there should be no more than two unknown forces. So in this example, we can move to joint B because now the member force at member AB is known and only unknown member forces are the forces acting on BE and BC. So we can draw the free body diagram and we can obtain the member forces T3 and T4 by analyzing this joint. Similarly, we can repeat the steps 3 and 4 until all the member forces are determined. So this is basically the procedure we have to follow to analyze a truss using analytical approach. Okay, let's do an example now and analyze a truss using analytical approach, and following these steps how we can obtain the member forces of a truss. Okay, let's do this example. We have given a truss A, B, C, D, E with the member sizes are 1 meter and applied 4 kilonewton vertical load at joint B, and we have asked to calculate the member forces of this truss using method of joints. So particularly we are using analytical approach to calculate the member forces of this truss. Okay, what is the first step that we should do? As per the procedure, step 1 is to calculate the reaction forces. Now, how can we calculate the reaction forces? We should consider the overall stability of the structure. So I marked the reaction forces as R1, R2 and R3. As the joint A is a pin support, one vertical reaction component and one horizontal reaction component is there, and joint D, it's a pin support, So I marked only one vertical reaction component R3. By considering the overall stability of this structure, we can apply the three static equilibrium equations. The first equation, the overall horizontal stability of the structure, we can apply that equation. So all the horizontal force components add together should be equal to 0. Now in this structure we can find only R2 is the horizontal component, horizontal load, so that should be equal to 0. So from that we can find the value for R2. And the second equilibrium equation, all the four force components adding in the vertical direction should be equal to 0. Now what are the vertical force components? R1 at A is a vertical force, and R3 is again a vertical force component acting at D, and there is a 4 kilonewton external load acting at B downwards. So the arrow that I make it upwards are positive, so R1, R3 are positive. Downward force 4 is a negative one. So the equation is R1 plus R3 minus 4 equals 0. So you can take it as R1 plus R3 equals 4. Now our third equation, a moment at any point of this structure should be equal to 0 for the overall stability. So I'll take a moment at joint A. So as per the equation, first we should consider what are the loads acting effective for the moment. So the external load 4 is creating a moment, a clockwise moment. So the distance from A to the load action line is 1 meter times cos 60. So 1 cos 60 is the distance, and my moment is 4 into 1 cos 60. It is acting clockwise direction, so 4 into 1 cos 60, a plus value. And due to the external force R3, it creates another moment which is anti-clockwise. So the force is R3, the distance to that force from A is 2 meters. So that total moment is R3 into 2. Because of its anti-clockwise, it's a minus value. So you can get the equation as 4 times 1 cos 60 minus 2R3 equals 0. Now that's my equation 3. From that moment equation, we can get it the value for R3, that is R3 equals 1. From equations 2 and 3, we can find the load for R1. So R1 equals 3 kilonewton. So applying the three equilibrium equations, we have done the calculation part of the reaction forces now. So the result is R1 equals 3, R3 equals 1, and R2 equals 0. Okay, once we calculate the reaction forces, what is the next step? We should calculate the member forces joint by joint until we calculate all the member forces. To select a joint, the condition, you know that there should be only maximum of two unknowns, right? Now, before moving to the joints, you can see in the figure that all the member forces I marked as tensile forces. The reason, hope you know, that if you remember the sign convention we used in our previous lectures, uh, that we consider tensile force as positive, compression forces as negative. So I marked here all the member forces as tensile forces, but this is only an assumption. If you prefer to mark the member forces as compression, no problem. But once you get the answer, you will realize whether actually the member is under compression or tension, right? For the way that I calculate the member forces, I just marked all the members as tensile forces. So now we should select what would be the best joint to start with. Now I have two options looking at this structure. Joint A, there are only two unknown forces, T1, T2, or I can start with joint D, only again two unknown forces, T7 or T6. But why I can't start the other three joints, B, C, or E? If I consider B, there are three member forces, T1, T3, T4. If I start with B, there are three unknowns, which I can't get the answer using the two equilibrium equations. Similarly, join C or E, uh, the thing is the same. We can't start with those joints because there are more than two unknowns. Okay, let's start with joint A. Right. Now, when I consider joint A, I treated that joint A as a free body diagram. Then that the member forces at joint A should be in equilibrium. So to make that joint equilibrium, all the member forces, the addition of all the member forces in vertical direction should be equal to 0. Addition of all the forces in horizontal direction should be equal to 0. So this is you can see the angle between members AB and AE 60 degrees. Then we can apply vertical equilibrium equation. So if I consider the forces acting in the vertical direction, 3 upwards positive, T1 sine 60, again upwards, that's positive, that's why 3 plus T1 sine 60 equals to 0. Now with the mathematics we can calculate the T1 from this equation. T1 equals to minus 2 root 3. Now what this minus sign giving us the message? Minus means, now initially we assume that T1 is under tension, but by getting a minus answer, now this member AB is under compression. Similarly, we can apply the horizontal equilibrium equation. Now we should calculate all the horizontal forces and add together, and all the addition of the member forces at horizontal direction should be equal to 0. T2 is one of the forces, and it's uh, uh, in the direction that the arrow I consider. In the similar direction, T1 cos 60. So adding those are the only two forces. Adding these two forces together should be equal to 0 to make the joint A under equilibrium. So from that we can calculate T2. Now there are T1 also in this equation, but we know T1 is minus 2 root 3 from the previous equation. So apply that and you'll get T2 as root 3. Is a positive value, that is T2 is under tension. Now analyzing those two equations, we can get it the unknown two forces T1 and T2, right? Now once we do that calculation, then we can move to the next joint. Now if I move to joint E, still there are more than two unknowns, because only T2 we know from the analysis of joint A. But joint B, we know T2, T1, but T3 and T4 are unknowns. So we can move to joint B and calculate using the equations, and we can obtain T3 and T4. So equilibrium of joint B, now we can draw the free body diagram for joint B. You can see T4, T3 and T1 there. T1 is a known value now, so we can apply the equations and obtain T3 and T4. Horizontal equilibrium, minus 2 root 3, that is for T1, cos 30, that create the vertical component of the T1, because that force is under in downwards. I'll make it minus in front of this equation, and also the next force component that using for the vertical equilibrium, minus T3 cos 30. Minus is because of downwards. T3 cos 30 is the vertical force component, and minus 4 is due to the external force downwards. So add all the three components should be equal to 0. There is only one unknown T3 in that equation, so we can get the T3 as minus 2 divided by root 3. Similarly, the equilibrium in horizontal direction, you can see the value, see the equation, minus 2 root 3, that is T1, which we get it from the previous joint analysis, and minus sign in front of that number is because of that's the other side of the direction that I consider, which is opposite to the direction that force acting, so it's minus. and T4 in the direction that we consider the arrow you can see. So that is positive T4, and also the force component from T3, that is T3 cos 60, is again in the direction that we consider, which is positive. So here T4 and T3 they are in the equation. T3 we have already calculated before, and by plugging the T3 value into the equation, you can get it T4 as minus 2 root 3. Now you can see T3 and T4 both are minus values, which means members BE and BC both are under compression. Then we should move to the next joint. Now I can move either to joint E, because we know T2 and T3, so only unknowns are T5 and T7, or we can move to joint C, which the unknowns are T5 and T6. I'll consider equilibrium of joint C. Just draw the free body diagram for joint C. You can see T4 is a known value now. T5 and T6, we should find it. As we discussed before, apply the vertical equilibrium, then you will get it T5 equals minus T6, and the horizontal equilibrium minus T4 minus T5 cos 60. That's due to the horizontal force component from T5, and horizontal force component from T6 is T6 sine 30. So adding together, for the equilibrium it should be 0. So using the previous equation, T5 equals minus T6, you can obtain what is T5, because T4 is a known value now. So T5 is 2 divided by root 3. Now if you know T5 from the above equation, you can get it T6 as minus 2 divided by root 3. Now that conclude the values that we obtained for T5 and T6 at joint C. Now we should move to the next joint, and once we do that analysis in that joint, then almost all the members are calculated when we do the analysis of the next joint. So I'll select equilibrium of joint D now. Now I can draw the free body diagram. So T6 and T7 and the external forces 1 there. T6 is a known value now. By analyzing the joint C before, we obtain the value for T6, and only value we unknown is T7 here. So we can apply the equation, the horizontal equilibrium equation. Straight away we can get the value for T7, because T6 is a known value. So T7 is 1 divided by root 3. So we can check the answer we obtained from the previous equations. We'll just try to do the horizontal equilibrium and see whether we'll get the same answer for T6. Now the T6 answer from this calculation, we'll get it minus 2 divided by root 3, which is the same value that we got it from the analysis of joint C, you can remember, right? Now all the truss is analyzed now using the method of joints, and we followed the analytical approach, and you can mark all the member forces which we obtain from these analysis as the figure in this slide. Now there you can see still I am using the same uh, the marking as tensile forces, but the values are minus, which means it should be in compression. So you can mark and you can give the answer just like this with the tensile arrow marks and with the true value minus or plus. You can put the value and you can provide the answer in this way, or more representative way. You can do it by changing the arrows. Now here you can see I have removed all the minus signs. Now only the value is there. Arrows representing whether the member sign tension or compression. For an example, AB is under compression. The value is 2 root 3. AE is under tension, that's why arrow sign that direction, but the value is root 3 for the tensile force. So likewise, both two methods you can represent your answers, but providing answer in this way, it's more clearer to you, I assume, but either way is all right. So that is how you analyze a truss using the method of joints by following the analytical approach. Now, hope this video helps you to analyze a truss using this method, and hope it is clear. If you do few more examples, you will get more familiar with this method of analyzing a truss. Thank you.